it's kind of funny because I put the thing more random numbers relative to a previous presentation of mine a couple of years ago, not the presentation right before me. Anyway, I have 3 sets of new algorithms out of many algorithms that didn't make it. The first one is based on trigonometric algorithms, and I did it because the challenge was, oh, you can't do random numbers with sine, cosine. Really? Okay. And then the other 2 are similar. They're single and multiple seeds of nested exponential algorithms, and I'll show you what I mean. To measure the goodness of that, I use a penalty factor based on generating 10,000 random numbers, iterated 5,000 times. And in 1,000 run, and each run I use different constants. And the penalty factor, which I've used in previous work, is a weighted sum of various statistical scores, like how close is it, because it's uniform, how close is the mean to half? So I take the difference and then I multiply by a penalty weight. And how close is the standard deviation to 2.88? What about the correlation, histogram, Bing chi-square, sign changes, and so on. So I calculate all these, and each one has a weight, and I add up. So, and I get a penalty factor. Of course, the lower the penalty factor, the better.
So that's the way you're
Yeah,
getting the
yeah,
quality of the
yeah. Now the famous random times 997 fraction, that scores about 148. So that's, and I've presented that in previous talks. So that's where, that's my standard. Anything below 148. The first set is, I use a constant A, and on a few of them B, although those did not make it well, and a constant S, which is slightly above 1. I played with it, and if I have it above 1, it seemed to do okay. A and B are randomly selected in each run. And I use the progressive sum of the random numbers. That's a new heretic concept. And I use sine and cosine because they cycle. Tangent, you're asking for trouble because it can go up. I need to control the range of the function, and sine cosine are ideal. And I use 1 to 3 initial seeds. The 1 and 2 seeds did okay. The 3 seeds was too much chaos for its own good. And here I'm presenting the top 5 ranked in best in the sign. The first one is seed 2 is the new seed, and is the fraction of A, constant A, over half times sine, sum of the seeds times the current seed plus cosine, sum of the seeds times the previous seed. Here I'm using 2 seeds, and that's the best algorithm in its a category, where A is 2.1 million and S is 2 times half, that's slightly above 1. And SM, of course, is the progressive sum of random numbers generated. And I obtain a penalty factor of 147. That's good. First, it's below 148, and it's even below 147 and a half. Because the lower you get, it's sort of like trying to get to absolute 0. It's very difficult. Just to give you an idea how to code it, you initialize it. You assign 2 initial seeds to seed 1, seed 2. You add them, put it in SM. You initialize the constants A and S. And then you start looping. Seed 2 is the current random number. I use the word seed, but it's the random. And you make a copy of it. And then you update seed 2 with the formula. And you update SM by adding seed 2 to it. And then you assign C2O to seed 1, and then you cycle. The second best one is the same formula, but I changed the constant A slightly. Was 2.12, now it's 2.16 million. And I get also 147.21, very good. Slightly above the first one, but it's still below 147 and a half and 148. 2.8. The third one, I replaced the cosine with sine, and then I squared it. And A is 2.1 million, 2.12 million, and I get also 147.25. So far, I'm doing good. Number 4 here, I go back to the original formula, and I have just changed the constant A again, because each run I pick a random A. Because originally I was curious whether A was like a specific value was like, you know, it has to be fixed. No, you can play with them. You can select different values. And I still get 147.26, still very good. And this one also, I have number 5, is the same formula. No, I'm sorry. Now it's A over half sine sum of the c times 2 over 0.5 cosine sum of the c times the previous seed plus s. So there's a slight shift. A is 2.056 million. And I still get 147.26. I'm doing very good. And here's the list of the rest ones, and you see this second column, the mean, and all the values are below 148. So all these algorithms are good. I asked ChatGPT, give me a random number generator with sine, and that's what it gave me, fraction of 10,000 absolute of sine times the c, the random numbers, times pi plus a constant. And when I ran it, it gave me a penalty factor of 150. I said, let me try to see if I can do better. So I replaced 10,000 with 1, 3, 5, 7, 9. They're all odd numbers. And actually, I got worse results. So the beautifully random number, 10,000, did well. Now I go to the single nested exponential. It uses a single seed, single random number, and it uses intermediate variables x1 and x2 as expressions of R, such that x1 and x2 are always at least 0, between 0 and 1 or between 1 and 2. This is based on a variant that I played with the calculator, fraction of exponential of exponential of exponential. The preliminary test showed it's a good test, but when I did the penalty factor, it jumped high. So I figured it was a good idea, but maybe a variation of it will give me good results, and it did. And here I have the fraction of exponential of x1 plus the exponentials of x1 and x2. This ranks number 1. And here x1 is a cubic polynomial of R, and it's in the range of 0 and 1. And x2 is a quadratic polynomial, and it's between around 1 less than 2. And R is the current random number. The factor is 146.1. Wow, that's the best in the bunch, yes.
How do you update the x1 and the x2?
In each cycle, because I'm updating the R, and each loop.
R goes into the x2?
Yeah, every time, yes. Yeah. This is the best. So it's not only below 148, it's below 147, it's below 146 and a half. So this one is the total winner. And this is how you could easy to code it. You assign the initial code to R. You calculate x1 and x2. Now here, when I change sometimes the expression, and I change how I calculate x1 and x2, and of course, the initial seed. So I have 3 variables, the main equation and how I calculate x1 and x2. It's different every time. And then I calculate x1, x2, and then get the next R. Very easy to use. The second best one, here I replaced x1 plus the exponential to 1 over x1. And here x1 is simply 1 plus R, and it's in the range of 1 to 2. x2 is still a cubic polynomial of r in the range of 0 to 1. And the factor is still 146, but 0.6, so it kind of jumped by half. Okay, so it's still below 147, 148. It's still good, but you can see the difference. And the third one here, I even simplify things. It's 1 over x2 plus the exponential of x1. And x1 is a linear function of r. x2 is 1 plus r squared. And they both are in the range of 1 to 2. And I also get 146.8. So I'm kind of inching closer to 147. Okay. The fourth one is I have x2 plus the sum of the exponentials of x1 and x2, of course, raised to an exponent. And x1 and x2 are both quadratic functions of r1. x1 is in the range of 1 to 2, and x2 is equal or greater to 1, but less than 2, maybe around 1.25, something like that. And I get still 146.9. I'm still in the 146, but I'm kind of getting closer to 147. And the last one here, I use square root of x2 plus exponential of x1 exponentiated. And both x1 and x2 are cubic functions of r, and ranging from 0 and 1. I get 146.93. I'm still under 147, but barely. It's still good. And here is the summary of the rest. You see the first three have a mean penalty of 147, and then you cross into the less than 147. Then you cross into the 147 area. Still always less than 148. And here again, it's in the 147 values, or below 148. The third set is the multiple seed exponential random number generator. I used 2 seeds, and I use 2 intermediate variables. Sometimes x1 is a function, most of the time x1 is a function of r1 only, and x2 is a function of r2 only, but at the end I start mixing both. And of course, these 2 intermediate variables are always equal or greater than 0. And the first one is I'm adding x1 and x2 and adding their exponents. And both are cubic polynomials of, x1 is a cubic polynomial of r1, and x2 is a cubic polynomial of r2. The first one is in the range of 1 to 2, the other one in the range of 0 to 1. And I get 147.25. That's the best in this. I was a bit disappointed because it didn't give me 146. It gave me 147. It's still below 148, but not what I was hoping for. And to execute, you initialize a previous seed to R1, the current seed to R2. You copy R2 into R20. You update the values of x1 and x2. You copy R20 into R1, and then you update R2, and so on. Rank number 2 here, instead of adding x1 and x2, I took 1 over x1 plus x2 plus their exponents. And both are quadratic polynomials of their respective random numbers. x1 is related to r1, and x2 is related to r2. And I also get penalty factor of 147.28. Still good, still below 147.5. The third one, here I use the same expression that I'm adding x1, x2, but I'm changing how I calculate x1 and x2. And they are both in the range of 1 to 2. And I get a penalty factor of 147.3. That's still good. The number 4, I use this, sorry, yes, same, but I also changed how I calculate the x1. Now I'm using a cubic polynomial of R1 to calculate x1 and a quadratic polynomial of R2 to calculate R2. And I get 147.3. That's still very good. And the last one is a little bit shorter. I just take the square root of x1 plus the exponential of x2, and then I calculate x1 here. x1 I'm mixing. I'm using R1 and R2, and the same thing. I'm mixing R1 and R2 in both equations to calculate x1 and x2. And I get a factor of 147.3. That's still good. It's under 147.5. And this is the rest of the list. If you look at the second column, the means, you're under 148. Very good. In fact, you're under 147.5. So, and here it's a little bit above, towards the end, above 147.5. So in conclusion, all the algorithm is good. The single nested exponential, to my surprise, worked better with a single seed. I thought in using more seeds would bring more chaos to the situation. For some reason, it did not work out. So anyway, thank you very much.
Now that you've got more complex operation,
Yeah.
in terms of calculator,
Yeah, this is like the DM42, the faster ones, the HP Prime, yeah. If you go to the older calculators like the 25, yeah, that's going to take.
yeah,
I would go with the 997 times whatever, because that's still very, very, very good. That's, yeah.
It's faster than Blazes, but it's trash.
I'm sorry?
It's faster than Blazes, but it's trash.
Well, I mean,
wait a minute now, how do you define trash?
Are you giving a second talk?
no, that's it. This is it, yeah. Thank you.
Okay, thank you, Namir.